This is Verbal. So in this section, we're going to be covering material that we would have covered during regular class time. And notice that we're going to be looking at molecular and ionic compounds. We're going to look at their structure, look at their property, and we're going to look at the differences between the different types. Now, this first type should be reviewed for you. Notice that we're talking about ionic bonds. Typically, you tell whether or not something has an ionic bond based on the fact that it has a metal present. It also has a non-metal present. So you want to pay attention to, does the compound contain a metal and a non-metal? And typically it is transfer of electrons. So the metal typically donates electrons to the non-metal. As a result, the metal becomes a cation, which is positively charged, and the nonmetal becomes an anion because it's receiving a negative charge. This causes an electrostatic attraction. So the cation is positively charged and it's strongly attracted to the negative anion. Now you have to be careful because some of these compounds actually will have polyatomic ions. And I'll tell you right now, ammonium NH4 plus is an example of a cation that is not a metal, but it forms a ionic compound. And I'll talk more about that later. Okay, the other type of bond is covalent. And notice that covalent, we're talking about a nonmetal. So usually it's two or more nonmetals, and they typically share their electrons. They do not transfer, so you got to pay attention to that. And the reason why is they want to have an octet. Now, when you have an octet, you want to make sure that each atom has 8 valence electrons around it. There are 2 elements that do not have octets, and that typically is hydrogen and helium. So you might want to include that information. Now, when we are talking about a molecule is slightly different than an ionic compound. It typically is 2 or more atoms that are bonded together and they are nonmetals. The 2 types that we typically have are polar and nonpolar covalent. And we will talk about when do you know which type you have based on your elements. Now, the way that we typically decide whether something is polar or nonpolar is we look at electronegativity. Please remember, electronegativity is the ability of an atom to attract electrons in a chemical bond. Now, this is different than electron affinity. I don't know if you remember, electron affinity is the ability of an electron to be attracted to an element, and they look at, does it require energy or does it not require energy? So this is not electron affinity. Now, you should know that the most electronegative atom is fluorine. And the reason why is it has a very tight attraction of electrons to the nucleus. And because of that, it has a smaller radius. So the smaller the radius of the atom, the higher the electronegativity. Now, our friend Coulomb's force of attraction, we're looking at how strongly are the electrons attracted to the nucleus, and that is based on distance. So if you have a smaller distance, you're going to have a greater force of attraction. So as a result of it, if you have a larger radius, you're going to have a weaker force of attraction. Okay, so you should know this generally, that if you go from left to right, that electronegativity increases. So as a result of it, the radius of the atom gets smaller and the electrons are held more tightly as an increase of that Coulombic force of attraction. Now, obviously, the opposite happens when you're going up a group. Electronegativity decreases because the energy levels are smaller. So as a result of it, the distance is smaller and the attraction that the electrons have to the nucleus are greater as you go up a group. Now, This is a very useful tool that chemists use to decide whether something is ionic or covalent. Now, I'll tell you, routinely, students struggle with this because the only way you can figure this out is if you have an electronegativity table. So notice that when you're going from 0 to 0.5, I've seen textbooks say 0.4. So anything that is greater than 0.5 is considered polar covalent. So what you typically do is you look at the two atoms and you look at their electronegativity and then you subtract them and you see is the difference greater than 0.5. Now notice that if it's greater than 1.9, we are now talking about ionic bonds. And typically that happens between a metal and a nonmetal. Now I'll tell you there are some gray areas. Occasionally you will see an electronegativity difference between two nonmetals and it's greater than 1.9. But most of the time it's a metal with a nonmetal. Okay, so here are three examples of different kinds of bonds. The first one on the left here is nonpolar. And typically when you're looking at two nonmetals and they have the same electronegativity difference, of course they're going to be nonpolar. So if you see an atom bonded with itself, I would automatically assume it is a nonpolar compound. Now, when you have a difference in electronegativity, remember fluorine is the greatest electronegative atom, hydrogen not so much. There's enough of a difference that on the left-hand side we have a slightly positive charge versus on the right-hand side we have a slightly negative charge. And notice that the cloud that surrounds fluorine is wider than the cloud that surrounds hydrogen. And that's because the electrons are being shared unequally. So it's like having that sibling that tends to hold on to something more than you. So fluorine is holding on to its electrons in the covalent bond more than it is hydrogen. Now on the rightmost side here we have ionic compound. So here sodium, which is a metal, gave up its one valence electron, and as a result fluorine gained that electron and it became an anion. Okay, so with polar covalent bonds, we have an unequal sharing of electrons. So as a result, the electrons spend more time around the atom that has a greater electronegativity. I think that's all I want to say on that. Okay, so here is an example of a molecular compound that has two atoms. They're the same atoms, and as a result, they have zero electronegativity difference. So they're considered pure covalent, or if you want to call it nonpolar covalent, you can also say that too. Here is a slight difference in electronegativity. By the way, I would just automatically assume whenever you see carbon and hydrogen bonded to each other, they're going to be nonpolar. I know in some textbooks they say that if it's 0.4 or greater that it tends to be polar, but definitely carbon and hydrogen are nonpolar. Here is a difference where bromine is slightly more electronegative than hydrogen, so as a result of it, the difference is 0.7, and this gives us a polar covalent bond. Here is carbon dioxide, and don't ask me why they didn't show the double bonds with oxygen, but it is what it is. So here we have, on the left, we have a difference in electronegativity, which is 1.0. So you could argue that the arrow of polarity goes from carbon to oxygen. You could also argue that it does the same thing on the right side. So please notice that this is a situation where we have a polar bond, but they're pointed in the opposite directions. And we'll talk more about that with intermolecular forces. Okay, here is an example of, we have a metal, which is lithium, and it's bonded to fluorine, which is a nonmetal, and as a result of it, that electronegative difference is 3.0. So it's greater than 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, 1.9, So I typically look at which type of element am I looking at? Am I looking at a metal? Am I looking at a nonmetal? And that typically helps me to decide if something is ionic. So if I notice that there are two nonmetals, I say, aha, it must be covalent. Because this is just a quick and fast method of deciding whether or not something is ionic versus covalent. Now, when we look at properties, ionic compounds have very strong attraction with each other. So as a result of it, their melting points are very high. So if you took salt and you tried to heat it up, you're going to notice that it is not going to decompose quickly because it has a very high melting point. And as a result of it, the solid is very hard. So as a result of it, it's very hard for you to I'm sorry, I don't know what I was going to say with that. Volatility. So when we're talking about volatility, the ability to go from a solid to a liquid to a gas, salt has a very strong force of attraction. So as a result, it wants to remain a solid. It does not want to become a vapor. Now, ionic compounds, I did have a lab last year where I had them pounding on the ionic compounds, and most of the time it is brittle. So notice that ionic compounds tend to be brittle, and it's because they break apart. Even though they do have a strong attraction, you can't pound them indefinitely. They will actually cause a separation in their charges based on their forces. So we're essentially creating repulsion by pounding on them. If you see at the bottom here, we have repulsion because pounding on them causes the positive charges to come in contact with each other, and as a result, they want to split apart. So notice that you cannot pound an ionic compound. You also cannot draw it into a wire. So when you see the term ductile, that is when you are drawing something into a wire. Okay, now this is something that you probably know already, is typically ionic compounds are soluble. Although you have to be careful because remember when we talked about KSP, there are salts that are slightly soluble. So you got to pay attention to their solubility product. They definitely conduct electricity. If you take a solid and you're able to actually melt it high enough temperature and you apply a charge to it, you will get conductivity with electricity. Now notice that if you have more ions in solution, the greater the conductivity. Now you might ask yourself, well, okay, isn't that obvious? Well, some people forget that if you have pure water is not going to be conductive because pure water does not contain ions. So as a result of it, you will not get conductivity. We'll talk more about that. So covalent compounds. Covalent compounds have a weaker attraction with each other. So as a result of it, there is lower melting points and there's also lower boiling points. So if you took sugar and you took salt and you put both of them in a frying pan, you're going to notice that sugar is going to melt faster and it's going to occur at a lower temperature than salt because covalent compounds have a weaker attraction. Now, you might notice if you were to pound on sugar versus salt, you might notice that sugar is actually a little more flexible than salt. This is also important too. Covalent compounds typically do not conduct electricity. However, we have to be careful because when you have ions forming, like you do with acids, you're going to have conductivity. So you have to be very careful when you talk about conductivity in covalent compounds. Okay, polyatomic ions. I am not going to go over all of the different polyatomic ions. you way back when had a chart that talked about the polyatomic ions. And I don't know if you remember the polyatomic ion quiz that I gave you. Um, Typically, you have nonmetals, not always. You could have nonmetals with a metal, and together bonded, they actually form an ionic charge based on the fact that they're missing or they have extra electrons depending on what's going on. Typically, polyatomic ions have covalent bonds. They could be nonpolar, they also could be polar. Okay, so crystals. Ionic compounds are not molecules because it's very hard to see where one part of the compound begins and the next part ends. So we typically call them crystalline and that they have unit cells. You may have heard the term formula unit. That's another way of us identifying and describing ionic solids. If you are interested in geology, you can see a lot of interesting shapes and crystal structures that ionic compounds will form based on their arrangement in space. So, ionic compounds want to maximize their attraction, and I don't know if you remember in the classroom I was showing you some big 3D models of ionic compounds. Their arrangement in space is based on this force of attraction. So they want to maximize the positive charge with the negative charge. So here's an example of salt. Um, Notice that one of the atoms is smaller than the other. Hopefully you can figure out which one is the smaller one. Please remember cation sizes are different than anion sizes. And salt itself wants to maximize the charge with the opposite. So notice that chlorine wants to be arranged in space so that it maximizes its location with all the cations. Here is what they call a unit cell. The good news is you don't need to memorize this. But if you do hear them use the term unit cell, it's not going to be something that is totally unfamiliar with you. Here's just another arrangement that atoms tend to make in space. Once again, you don't have to memorize this. Here's another example where they're trying to sandwich the different ions in space. Likewise, here's an additional example. I'm just breezing through that because you don't have to worry about knowing exactly what unit cells you have to have. Just get familiar with the term. Okay, this is my last section for this set of notes. So metallics. Metallic solids, we technically don't call them covalent. And you'll see in a minute why we don't call them covalent. Typically, what happens in a metallic bonding, we have nuclei that are sharing delocalized valence electrons. So when you have a metallic bond, it's typically one or two metals, and their nucleus or nuclei are sharing a collective sea of electrons. Now, notice that they have two examples here where they have a melting point for sodium, which is 97.5, but notice that iron has a melting point of 1500. So this is just showing you that the higher the boiling point, the stronger the strength of the metallic bond. So this is what I was referring to. All these positive charges represent the nuclei, and then these black dots that they're trying to show you here are the example of the sea of electrons that typically are shared all over the place with these nuclei. Now, the benefits to metals doing this is that they are very good at conducting electricity. So you may notice that some metals are better at conducting electricity than others because they can share their electrons more freely. Also, heat. So a lot of cooking materials are specific types of metal. If you're really into creating sauces, um, you're going to find a lot of high-end pans are made with copper because it's very good at conducting electricity. The other thing is you can pound metals and they will not break apart because they're able to keep their attraction together with the electrons that they are sharing. And the same goes with turning metal into a wire. Metals are very good at being pulled into wires without breaking apart. Now, this last piece here where they talk about directional bonds, it's a lot harder to show the direction of the metallic bond based on their sea of electrons. Okay, I forgot we had a few more things we had to add here when we talk about metals. Um, I'm less concerned about solution, solvent, and solute. I'm assuming you already know that. I'm more concerned about alloy. It's really important to remember that alloy is usually two or more metals. So I don't know if you remember the copper penny experiment. I've done it for a lot of the open houses where you take a copper penny and you plate zinc on the outside and then you heat it up. And the amazing thing is that the copper is replaced by some of the zinc atoms to create brass. And that is an example of an alloy. So one example of an interesting alloy is interstitial, and that is steel. We as a human population figured out to replace or fill part of iron with carbon, and as a result of it, it became much more rigid and much more resistant to rusting. So, as a result of it, when you replace or you add another element, you actually get a bonus as a result of it with the properties. So, carbon with iron gives you steel, which has more favorable properties than just iron. Okay, I'm going to skip this part here. So substitutional. So this is the brass penny that I was talking about. Now the way this works is you have to have similar radii. So copper and zinc, if you look at them, they're close to each other in the periodic table. So as a result, their radius is very similar. And we were able to figure out a way to replace copper atoms with zinc. And as a result of it, we get brass. So notice that they're very similar in size, and as a result of it, we get a nice substitutional alloy. Okay, so that is all I need to review with you right now, and come back for a new topic.